Hi, it's time for another math easy solution. To discuss further into polar coordinates, and now look at example 12 again and look at question B of example 12, and basically it goes over the Limaçons and analytical proof that I went over in part 1, and I will just do part 2, which looks at question B, which is this one right here. So make sure to watch my last video on question A, which is part 1. So let's look at part B right here, which states, also from example 11, it appears that the Limaçon loses its dimple when C equals 1/2. Prove this. And again, remember the Limaçon from example 11 was this one here, R equals 1 plus C sine theta. C is the constant, then we have to basically graph it using different values of C, and again this is a polar curve. So recall from example 11, these were the charts for different values of C. Their C is 2.5, you have a loop, and this one is just a cardioid when C is equal to 1, or a heart shape. Then when you have the negatives, it just flips upside down like that. So let's look at this again. So it appears that it loses its dimple at C equals 1/2. So look at this. Basically, when C is equal to 0.7, for example, here has a dimple there. And then when C equals to 1, it's a sharp point. So that's sharp, but now it's a dimple. And here 0.5, this is flat right there. It's flat, or it could be considered as basically no dimple, because it's just a flat line. And here, as you can see, this part, this one is just rounded, so there's no dimple there either. But so we want to prove that at C equals to 1/2 or 0.5, that it's flat and there's no dimple there. So let's go about solving that. So if we just scroll down here, we'll start trying to prove it. So part B, not A. Yeah, just fix that up. So for C is between 0 and 1, that's where there is a supposed dimple there. So the C is 1 is not, and then you have all the way to 0 is just a circle. So we'll just consider that range from 0 to 1. So in between those. Yeah, so basically the dimple, if it exists, is characterized by the fact that Y has a local maximum at theta equals 3 pi over 2. If you scroll over here, if you look at the angle, this is actually, yeah, that's just 3 pi over 2. So theta equals to 3 pi over 2. That's just on that line across there. I believe that's 270 degrees. And again, you could see this here. I'll draw this across here. So what we have is this rotation. This is theta equals to 3 pi over 2. And how the shape looks like, the Limaçon looks something like this. And then, yeah, so it has a dimple here. So this is a local maximum over there. So point that out. This is local max. So yeah, this is something we must have. And this is a local max for the Y. If we put this onto a Cartesian coordinate system on the X, Y axis like that, and also recall converting the polar to the regular Cartesian or parametric equations, what we'll get is, if this is X, Y, and we have a point here, let's say this distance is R, that's theta, then I'll just draw a right angle. This is R, theta, and polar coordinates, but also this height, we could have Y, and then this bottom part here is X. So again, if you want to write the Y function of this, we could use trigonometry. So sine theta equals opposite over hypotenuse Y over R. And now we get, move that over, we have Y equals to R sine theta. And yeah, I'll just write that over here. So we have Y is equal to R sine theta, where R equals to, remember R is just a Limaçon, 1 plus C sine theta. So we have 1 plus C sine theta, and then times it by sine theta. Now what this equals to is sine theta and then we just multiply that inside sine theta, and then we have plus c sine theta squared. So this is what our y function is, as basically the y-axis or y vertical component of the coordinates in terms of the angle theta. So now to determine if there is a local maximum, we can use the second derivative test. Make sure to watch my earlier video on that and put that in the video link below. So recall the second derivative test. Recall what we have is if we had, let's say, a function like this. This is, let's say that's x, and this is y, and you have a curve like this. So that has a maximum there, or a local max, or whatnot, etc. This could be a local, that could be an absolute, still local, wherever that region is. So what we have is if this curve is f of x, or y equals f of x, then this point here, let's say that at this point we have a, and now there's a flat line at the top here because it's a local max. So that means that the derivative f of a, this is equal to 0. It's a flat line, and now since this is curving downwards, the rate of this slope is decreasing. This again means we have the second derivative, f prime of a is less than 0. It's negative, so that it's decreasing the rate of increasing that, or just the rate. The rate is decreasing in value. So it goes from 0 and is decreasing. This one is going up, but it's decreasing. It's curving down. So we have that concave downwards. Yeah, so thus we need to find c values where dy over d theta, again this is just a derivative in terms of theta, and it's the same thing. It's the same thing if we were working with the regular Cartesian or in polar coordinates over here. For example, the y, as you're rotating across this way, we want the exact same thing across. Both of these are moving in the same direction, x and this polar coordinate there. As it's moving towards here, we need this decreasing and also flatlining like that. So even in terms of the parameter theta, it's the same thing. We need to make it have these characteristics where the derivative is 0 and the second derivative is negative. Yeah, so thus we need to find c values where dy over d theta, the derivative equals 0, and d squared, or this is second derivative, d squared y over d theta squared, like this. Yeah, that's the proper way to write that. That's just y double prime of theta. And this is again at that point theta equals 3 pi over 2. Yeah, but first what I'll do is first recall, so before I take the derivative, I want to find out these values for sine and theta. So if we have theta like this and this is y, just recall the curves for sine and cosine like that, and this one is just sine theta. And recall that the point here, this is at 3 pi over 2, I'll write it over here, 3 pi over 2 is at this point, and when you go downwards there, this is in fact negative 1 like that. Yeah, so that's at this point across. So recall that sine of 3 pi over 2 equals to negative 1. So we'll use that for reference. And now for the cosine, because we're going to need that in a bit, it's just like shifted version of the sine. So it goes something like this. It goes up and then it goes downwards there, and it starts repeating itself, and it goes on the other side. So we'll just deal with this part here. So at this point there, again, this is the, and then it curves back, this is the cosine theta, or function. And now at this point here, or y equals cosine theta, and then at 3 pi over 2, we have this value there. That's just cosine 3 pi over 2 equals to 0, like that. Yeah, so now that we have that, I'll just write this y equals 2 over there. Yeah, so now that we just have those referenced, thus we can start solving our function over here. So y equals sine theta plus c sine squared theta. So y equals to sine theta plus c sine squared theta, like that. Now we just take the derivative, y prime equals, again, dy over d theta. This equals to, derivative of sine is negative, or actually it's positive cosine, so cosine theta. And now the derivative here plus c, and then the 2 goes down, so we have, I'll just put the 2 over here, 2c, and then sine, which is going to be cosine theta. Actually, we need to put the sine first. So to put the 2 down, and then using chain rule, derivative of sine is cosine theta, like that. Now we could simplify it. My calculus book just simplifies it, but I rather just plug in our known values over there. So for this is going to be when we plug in cosine 3 pi over 2 plus 2 times c times by sine 3 pi over 2 times it by cosine 3 pi over 2. Now we can just begin plugging in our values. Remember, cosine 3 pi over 2 is just 0. So this equals 0, and then this one, well, that's 0 as well. That just goes all to 0, so we can ignore that. So plus 0. This equals to 0 for all c values. Or instead of writing all c, I'll just write for c is an element of all real numbers. That's usually how you would say it, just for all values. Yeah, so it's equal to 0. So the derivative for the local maximum test, that equals to 0, which is good. And now the next step is y double prime. This equals to d squared y over d theta squared. That's the notation for it. I believe that's a Leibniz notation or whatnot. So anyways, so now that we have that, this equals 2. Now take the derivative of cosine. That's just negative sine theta plus, now we have to use product rule. So these are constants, so we just put a 2c there. Derivative of sine theta is just going to be cosine theta. So now we have 2 cosines, cosine squared theta. And now we're going to have on this side another 2c, and then we have a sine theta, and then the derivative of cosine theta is negative sine theta. So we put a squared there because there's 2 signs now. Now we put a negative, so we have negative 2c, like that. And again, instead of simplifying it, my calculus book does up, I'll just plug this in. So negative sine 3 pi over 2 plus 2c times cosine squared 3 pi over 2 minus 2c times it by sine squared 3 pi over 2, like that. So now that we have this, we can just plug in our values. Remember, sine 3 pi over 2 is negative 1, and then cosine is 0. So we have negative 1 plus, this is 0, that just goes to 0, and now we have on this side negative 2c, and now this is a square, so we have negative 1, that's what sine is, and then squared, which makes it positive. So this equals to, that's positive 1, 2 negatives make a positive, so now we have negative 2c, that's just positive 1, so that is what our double prime is, like that. Yeah, so now if we have a negative, so if y double prime equals to 1 minus 2c is less than 0, if it's negative, for the c values for that to happen, we'll move this on the other side. We get 1 less than 2c. Now we can just divide the c out, so we'll move that over on this side. So c is going to be greater than 1 divided by 2, 1 over 2, like that. Yeah, so thus we have a local maximum only when c is greater than 1 over 2. Yeah, so thus we could sum that up. So thus, basically for c is greater than 1 over 2, yeah, this is at theta equals to 3 pi over 2. Yeah, we have y prime in terms of theta equals to 0, and y double prime is, well, negative, is less than 0. So thus we have a local maximum there. I'll just write local max like that. In other words, we have, i.e., a dimple. So like that, dimple. And now we could just check at our, basically at c equals to 1/2, so that's one's greater than it, and you can even double check at c is greater than 1/2. We have y double prime equals to 1 minus 2c, that's that formula above, that equals to, equals 1 minus 2, 1/2, the 2's cancel, 1 minus 1, 1 minus 1 equals to 0. In other words, this is a flat line. It's not increasing or decreasing the rate or the first derivative. So flat line, no dimple. So there's our proof for that. So that's our proof, but we can go further. So similarly for the negative side, where c is between -1 and 0, and we could look at that over here. So let's just scroll up. So between -1 over here, so that's a sharp point, that's just a cardioid or a heart. And now we have -1 is between -5. Here we have another dimple that's upside down, so this is another dimple over there. And now as c is -1/2 or 0.5, it's a flat line. I'll just put arrow to this over there. So flat line, no dimple. So we're gonna quickly prove that one. You can do the pretty much the exact same thing. So similarly for c is between -1 and 0, y only has a local minimum at theta equals to pi over 2, and this is again indicating a dimple. For c is less than -1/2 or 0.5, and again this is at the different angle across there. So this is at over there, or here's the dimple there. This is rotating it by pi over 2, or 90 degrees, like that. So that is the angle there. So let's just scroll down and go about solving this. So this one's a local minimum as opposed to a maximum. So if you were to graph that in polar coordinates, we have over here as a dimple going upwards like that. I believe the rest of the shape looks something like that. And this is just a right angle, which is just pi over 2 or 90 degrees. And then this is again flat line, so we have our y prime equals to 0. I'll put a y there, x there. This is in terms of theta or x in this case. And also, now this time it's rotating upwards, so it's increasing. So basically the rate is going to be increasing upwards, or it's concave up. So we have y double prime is greater than 0. So that's the only difference. Only difference is it's greater than 0. Now we're dealing with pi over 2. So let's just get the reference values above here for pi over 2. And pi over 2 is actually across here. And that is at this 1 value. So now we have sine of pi over 2 equals to, 1. And for a cosine, that is again 0. So cosine pi over 2 equals to 0. So as opposed to -1, now we have a 1 over there, and I'll circle those. Put this a bit neater. So let's just go over there and write this for reference again. So sine pi over 2 equals to 1. Cosine pi over 2 equals to 0. And now we can just solve for the derivative. Y equals dy over d theta. This equals to, if you recall from above, we have cosine theta 2c sine cosine theta, like that. So let's just write that out. So cosine, now let's write pi over 2 plus 2c sine pi over 2 cosine pi over 2. Plug those in. This is just going to be, put it over, over here. This is going to be cosine pi over 2 is just, cosine pi over 2 is again 0, and there's a 0 as well there. So that just equals to 0. And this is for all c values, or c element of all real numbers, etc. So now for y double prime, we have y double prime equals to d squared y over d theta squared, like that, in that notation. So now that we have that, let's look at what that one was again. So negative sine theta 2c cos squared. Now we have a negative 2c sine squared. Let's see if I memorize that. We can just look at that and derivative of that. So cosine pi, cosine negative sine pi over 2, and then we have a plus 2c times it by cosine squared pi over 2. We're just plugging those values in. And then a minus 2c times sine squared pi over 2. So those values now, the difference is going to be, here. So sine, that's just going to be negative 1, plus this is going to just be 0, then minus 2c times it by here, sine squared of 1, that's just, well, 1. Yeah, so 1 squared is just 1. So now that we have that, now we can, that's negative there. So now we have negative 1 minus negative, minus 2c. And this is our double prime like that. So we wanted to see when the derivative is greater than 0, so y double prime is equal to negative 1 minus 2c. It's greater than 0, and now we can just solve for a c at that time. Move this on the other side. We get a negative 1 greater than 2c. Divide the 2 out. We get now c is c is less than negative 1 divided by 2. So negative 1 over 2. So there is the local minimum now. And we could sum that up. So thus, thus for c is less than 1 over 2, a negative 1 over 2, at theta equals to pi over 2, we have y prime equals to 0, and y double prime is greater than 0. So that means we have a local minimum. So write local min. And again, i.e., same exact strategy as above, i.e., it's a dimple. Like that. And again, for c equals to negative 1 over 2, what we'll notice is that, well, the y double prime equals to negative 1 minus minus 2c equals to negative 1 minus 2 negative 1 over 2. So this equals to negative 1. Now the negatives cancel, the 2's cancel, becomes positive 1. That equals to 0. And again, same exact thing. We have a flat line like that, i.e. no dimple. And there's our proof for that part there. So yeah, that's all for today. If you learned from this pretty extensive proof video, just to show you how you could prove if there's a dimple or not by using the local min max and using the second derivative test. And also make sure to watch out my earlier video, put that in the description below. And it was all for today, as some pretty interesting stuff. So again, there's that flat line, no dimple, and then there's a dimple there in between. In between negative 0.5 and negative 1. And it's exactly reverse of these ones, where it's 1 and 0 between those. Between 0.5 and 1, for the dimple. So yeah, it loses its dimple when c equals 1/2 or negative 1/2. And it was all for today. Like always, you can download these exact notes in the link below, and also view these notes on Steemit. I'll be uploading them shortly after I upload this video. Anyways, thanks for watching, and stay tuned for another Math Easy solution.